The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Okay, good afternoon. Let me quickly go through an overview of my presentation. I want to talk about crushed-film mineral filler. As Eric mentioned earlier in our document, it's called dust fracture. And so I'm going to go over some of the engineering properties, compressive strength, flexural, and shrinkage. Then my proportioning example is going to perhaps fill in some gaps that Eric didn't get into the details. Want to talk about some of the batch plan adjustment that is necessary, and then I will also touch on the quality assurance of this material. So what is this material? As Eric had mentioned earlier in the document, it talks about this minus 200 material, exceeding 65%. And what I want to focus on is a special a wet mineral filler, and it's blended with manufactured sand. Well, in reality, it's really a manufactured sand that hasn't been washed, and then there's a tremendous amount of minus 200. And my aggregate guys call it number 10 screenings, and I guess it's a pretty common term in the aggregate industries. And the minus 200 amount is ranging anywhere from 14 to 20%. So, for the rest of my presentations, I'm just going to call it number 10 screening. So, you walk into any other quarries or any of the crushed-film quarries in the country, this is a very common sight. See this pile of material, and the reason it's in a plant because nobody wants it. So it's a waste material, and this picture here has a loader on the top. I think it's a Caterpillar, something like 950 or something like that is, for scale. So there's a big pile here. Occasionally, there might be some jobs that require fill material, and so you put a dent into it, maybe give it away, and if you come pick it up, we'll give it to you, that kind of thing. So the gradations examples here, number 10 screenings. In this particular one that I have is the minus 200 is 14.8%. In contrast, the natural sand that is in my system, this particular one has 0.3% minus 200. Look at the difference in Fineness modulus, number 10 screening, obviously 2.92 on the FM, which is very much coarser than a natural sand 2.51. And one would argue that actually this sand here is actually a lot finer, perhaps finer than ideal. And the marriage of these two materials actually produces a very good combined fineness modulus. So as I mentioned earlier, it's a waste material. There's tremendous cost incentive or economic incentive for ready-mix producer like myself to try to utilize this material. And just to quickly go over some of the cost figures, and obviously this cost savings here, we're looking at using the reference mix. All this is done with 564 pounds of Portland cement. With this 35% number 10 screening, so cost savings of $2.27, and then 45% up to about $3. And obviously all this saving is going to change tremendously depending on what you pay for natural sand. I would say in the Washington, D.C. area, $24 a ton for natural sand is pretty high. And that's not the highest we pay. And a lot of it is because, we're a little bit further away from the ocean, and the trucking cost is pretty tremendous. So that's that. And real quickly. So number 10 screening, is that a good concrete material? And that's a very fair question. And with that, I want to rely on the research that was done at the University of Texas. And Dr. Fowler was under his direction, and there was a lot of good research publication that came out of that center. And this particular one that focuses on using number 10 screenings The research gathered about 10 different sources, number 10 screening representing different geologies across the U.S., and each of it fails ASTM C33 sand gradation band. Now, one of the things I want to emphasize, this publication's been out for, 10, 15 years, Dr. Fowler, something like that? Yeah, so it's been out quite a while, and here we are. I'm just one of the ready-mix producers trying to commercialize and try to utilize data in everyday concrete that we use, and we've been very successful at it. So, quickly, these are the gradations of the -200. We're looking at something ranging from 4.5% -200 all the way up to 16.7%. In contrast, the natural sand has a -200 less than 1.5% -200. So if you look at the compressive strength with a fixed water cement ratio, it's good news in terms of this dust of fracture and what it does to concrete. And the compressive strength is higher compared with the natural sand. However, if you go with a fixed slump, the situation reverses with the majority, in fact, most of the screenings having a lower strength than the control. So what he's suggesting when you say fixed slump, that means that you let the water content vary to reach a particular fixed slump. So what this two data set, the graphs are suggesting is if we are able to maintain the water to cement ratio, the compressive strength is going to be very, very good, very decent. And so there's a water demand issue, so to speak, for those ready-mix producers that we've got to be cautious of. Then what about shrinkage? Well, so again, with fixed water cement ratio, you still have some of it have greater shrinkage than the reference. But let me point out this number here, 0.03% shrinkage. Okay, in a lot of specifications in engineers' designs and what have you, they would consider a 0.03% shrinkage as the upper limit. So while the natural sand has lower shrinkage than the manufactured sand, but all in all, even with this, this number 10 screenings, that the shrinkage is well below the specification, most specification limit. Likewise, you look at the fixed slump, again, you got a different shrinkage performance and so forth, and again, they're all less than 0.03. What about the flexural strength? So if you look at this flexural strength here, again, fixed water cement ratio, you're getting some really, really good increase in flexural strength. So at this point, I want to bring up an issue. Why are we so concerned about flexural strength? What about shrinkage and all that? Okay, so one of the things that we're concerned about is cracks in the concrete, right? Somebody call you, customer call me, says concrete cracks. I say, I didn't put crack in the truck before it leaves the yard, so why are you calling me? But from a technical standpoint, when concrete shrinks, it creates a tensile stress on the surface. Okay? So if the tensile stress is greater than the tensile strength, which is a lot of times reflected, the tensile strength is reflected in the flexural strength. And so if the tensile stress from shrinkage, for example, never exceeded the tensile strength capacity of the concrete, then you're not going to get any kind of cracks, right? So looking at this graph here, you will know that, well, obviously with the increase in flexural strength or the tensile capacity of the concrete, then there will be greater resistance to cracking due to shrinkage. Now, Eric went through and gave you an overview on the mixed proportioning in the ACI 211.7 document. And so I want to fill in some of the gaps, get into a little bit more details. Now, one of the things that we need to consider is here's a dust of fracture. And the particle shape is not going to be rounded like natural sand, okay? And the particle shape is, as my rock guys, my aggregate guys tells me, he say, hey, it depends on the rock. If it's granite and trap rock, which are much harder rock, you tend to get more flat and elongated pieces. And that's, versus natural sand, we are very rounded and like marbles. And natural sand obviously takes less water to achieve a certain mobility as reflected in the slump. Then softer rocks, you get much better chance, like limestone, are more rounded aggregates. Then there's another variable in terms of particle shape. What about a crusher type? Okay, and the two primary crusher type, one is called a VSI, which is vertical shaft impactor, and that tends to produce more rounded aggregates. And then the jaw crusher, the particle shape is more follow the line of the natural cleavage of the mineral. Well, then, as I said earlier, if we can marry up this material with natural sand, we get some really good material. And that's the solution, is to blend it with natural sand, taking advantage of some of the natural sand, taking advantage of some of the better properties from number 10 screenings. And so, in our document, you'll find that there is this concept of combined fineness modulus, and you see this table in the document. Nothing more than just a simple weighted average of the gradations and at different blending ratio. And so in this particular case, if there is a specification limit that limit the amount of minus 200, for example, if you're dealing with 5% maximum amount allowed for the minus 200, then you're not going to exceed 30% number 10 screening, for example, somewhere in the 30% range. So this is very useful. What is more useful, as I mentioned earlier, is coming up with a combined fineness modulus, because that's what you're going to need in mixed proportioning. You see this very, very familiar table in ACI 211.1, and with the fineness modulus, you can at least get the coarse aggregate. You can determine the coarse aggregate content that you need. So again, going back to the examples that I gave earlier, 564 pounds of cement throughout, and with 57 stones. And as you can see, the 28-day compressive strength, they're very, very comparable, okay? But this is done with fixed amount of water contents, constant water-cement ratio. But you see the slump decreases from the reference 6-inch slump, 4.75. The 6-inch slump is probably close enough that we could probably add a little bit more admixture and get it up if we so desire. But for example, as a residential mix or commercial mix or whatever, with this kind of compressive strength, is certainly 6 or 7-inch slump is really plenty of workability for the concrete finishers. And if we figure out what the minus 200, the amount of mineral filler, plus the cement that you add to it, you have a total powder content of somewhere in the 640, 661. So in other words, going from a natural sand reference, we're adding more fine powder. And my finishers really like to get the mix from me because I gave him plenty of cream that he can finish it and cover his slab and go on and save some time. And of course, I don't tell him that it's got manufactured sand in there either, because he's going to be not very happy if he hears the word manufactured sand. Anyway, so here, as you see the coarse aggregate 57 stone, I had some reduction in the amounts of stone based on experience, based on my experience with the particle shape of this particular 57 stones. This 5% down here is not correct, but somewhere there is some slight reduction. But you'll find all these out in running your trial batches, correct? One of the things I want to point out is the admixture dosage. In the ready-mix world and the admixture world, we like to use ounces per 100 weight of material. Okay? So traditionally, it's ounces per 100 weight of cementatious material. But in the case of when you're using a number 10 screen that is so rich in mineral filler, we need to be considered ounces per 100 weight of powder. Okay? So in this particular case, if I want to keep the the water reducer, WR stands for water reducer, at 4 ounces per hundredweight relative to the cement content. And when there is an increase in the powder content relative to the Portland cement, I'm going to have to up the ounces per hundredweight to account for the extra powder and so forth. And likewise, if the concrete is air and train, you got to account for that in your air and entrainment dosage as well. So I want to touch on the operational or batching considerations. The wet manner filler has some of its unique challenges, but can be overcome with not tremendous difficulty. Let's consider what is going on. In a lot of my plants are 40, 50 years old, but even in newer plants, a lot of plant designers for the aggregate bins, they were designed the bin to slope at 45 degrees at the bottom, okay? So, and that's just great if you're using natural sand. The angle of repose is, in this particular sand, is 38 degrees at 5.2% moisture. And the bin is 45 degrees. So the material is going to move very well by gravity feeding it into the mixer. In contrast with the number 10 screening, this particular source has a 44 degree at 4.2% moisture. Now, one of the things that you need to know is that if the moisture were to go higher, the angle of repose is going to increase. It's true in natural sand as well as in number 10 screening. But there's an added challenge in the number 10 screening. It's not all angle of repose in terms of movement through the bins and in batching, because the number 200, the mineral filler also creates some stickiness to the material, okay? And so you're going to have batching, and the batchman will be calling for 450 or 800 pounds of number 10 screening, and the material is not falling. Okay, it's problematic. So one of the things that we do in a plant, recognizing that we want to have bins greater than perhaps 45 degree natural angle of repose, or at least you got 4 sites in the bin, pick the one with only 2 of the sites that are sloped at 45 degrees, and the other 2 sites slopes at 90 degrees, voila, the material is moving a whole lot better when you have that simple change in bin configuration. Well, we also found very helpful from, I think this is from this particular manufacturer, what they call an air cannon, okay? All that is a high pressure tank. You're feeding a compressed air into it, somewhere at 80 to 125 PSI, and if there was breaching that occur, then a batchman can hit a button and it quickly releases high pressure compressed air to fluidize the material, and we find this to be very, very helpful in the batching process. Well then, let's get to the caveat emptor, buyer beware, okay? Not all number 10 screenings are suitable for concrete, despite what I'm telling you, touting the benefits and so forth of number 10 screenings. And this is no different than any material, right, that you use. As part of the buyer or technical services people, you just have to find out what the limitation of each material is and use accordingly and adapt it to your mixes. How about clay in crushed stone? Ever heard of clay? We know that there's clay in natural sand. We know that. Is this outlandish to say there's clay in crushed stone? Well, that's something that I learned when you work for an aggregate company. They'll tell you this, yeah, there is clay in crushed stone. And why didn't you tell me when you were, when I was just a ready-mix customer? So, but anyway, so there's this clay mineral group called smectite. And the worst actor in that family is marmorillonite, okay? What it is this is a depiction of what that is. You got sheets of molecules, and in between the sheets of molecule is just an open space and for water molecules to migrate into it. And there's no end in sight, something like, I don't know, it expands 4 or 5 times its volume. So imagine you have substantial amount of this clay in the mix, all your mixed water is going into the smectite, and you know, you don't have enough water to create your slump and so on and so forth. So smectite is bad. But there is actually a screening test called the methylene blue value test. A very new standard just got published the last couple of years. ASTM published a standard called ASTM C1777, and frankly, I wasn't aware that this was published until I was preparing for this presentation. And find it to be very, very interesting. In there, there is a note 1 that is very, very informative. It contrasts and compares the ASTM standard testing versus the other more established testing methods like Astro T330, and this is, I guess, is the European standard. And what is fascinating that each test method uses different size fractions, and ASTM C1770 used material as less than number 4. And what is methylene blue? Methylene blue is actually from a pharmaceutical industry that is a dark blue color when it's concentrated, but it has the ability to be absorbed. And when it absorbs, the blue color, the intensity of the blue color actually reduces. And ASTM C1777 is a much better method because it uses a special colorimeter, okay, and it shines a special wavelength to it, and you can actually measure the amount of absorption. ASTO is more of a subjective test, and so on. But anyway, well, the one thing that you should know is that when you have a high methylene blue value, that means there's more smectite in the number 10 screenings. So in conclusion, I hope you understand that certain number 10 screenings can be properly proportioned for a concrete mixture, and this 211.7 document is very helpful in that regard if you have a desire to check it out. And you may have to do some batch plan modifications to accommodate the uniqueness of the number 10 screenings to make sure that the material flow properly in the batching process. So that's all I have.
Thank you very much, Teck. Maybe one quick question, if there's anyone. Yeah, yes, sir.
Right.
Back in the IPAR study, where you had the natural sand and then the other materials, on a lot of those, when you looked at shrinkage or other things, some were above, some were less. Wouldn't we find that much variability even in the natural sands if they had tested